Today we're going to talk about problem 4.1 from chapter 4. So in this problem, we're asked to define these elements in this diagram over here. But it's also a very good problem to learn about what different elements are in a DC circuit. Sorry, just forgot to add that. So here is the schematic that I redrew from the actual drawing, the actual problem. And here are some circuit elements that I would like to go over first. So first and foremost, there are three different categories of DC circuit elements. So there are the independent sources, which they tell you specifically that, hey, I am this much value. So they tell you, for example, the independent voltage source tells you that, hey, right here, right now, I am going to be, I guess, 18 volts, for example, as shown in the problem. And a independent current source, like the one shown in the problem here, tells you that the current floating over here is going to be 5 milliamps, right? So, yeah, so this is an independent voltage source. I'm not going to write out the whole thing. This is the independent current source. And these two are dependent sources. So this one is the dependent voltage source. This one is the dependent current source. And like their name suggested, the dependent sources depends on another part of the circuit to determine what voltage or current they are. So for example, if we look at the dependent voltage source over here, they're telling you that, hey, my voltage is actually dependent on the current that floats over our 2 resistor, right? So there, you have to look elsewhere in the circuit. And the last one, also very important, is our resistor. So the resistor is easily the most important and most fundamental circuit element that we need to know, because it's almost in every single problem you're going to encounter in this chapter. So this is a resistor, and this is a dependent voltage source, dependent current source. These are just the abbreviations, but you can write them out if you want. And then now let's talk about what branches are. So a branch is basically circuit elements that you see in your schematic. So in the schematic here, we have a total of 7 resistors, right? So that's 7. And then there is one independent voltage source. There's one independent current source. And there is a dependent voltage and also a dependent current source. So that's +1, +1. So 7 + 1 + 1 + 1 + 1 is equal to 11. So there's a total of 11 branches, or 11 circuit elements. And branches with unknown currents. So which branches or which circuit element tell us exactly how much current is at that branch? So like we explained earlier here when we talked about circuit elements, we mentioned that only the independent source tells us that. And specifically, if we want to know about currents, we should probably look at independent current source, right? As the name suggested. So as we defined earlier when we saw part A, there's only one independent current source. So there's only one place in this entire circuit where the current is explicitly given to us. So we can say that there's 10 branches with unknown current, right? 10 branches, branches. And part C, we're asked to find essential branches, which actually I'll skip part C and D. We're gonna come back to them. We should probably define what a node is to begin with. So a node is basically a connection of different circuit elements. So it could be a little bit tricky. So if we look at a simpler example down here, so a node is basically a connection between two circuit elements. You can think of it as the junction between two circuit elements if you want. So between this independent voltage source and this R1 resistor, that is a node. And then down here, when we look at the 5-volt independent source and the R2 resistor, this entire part, despite the fact that there's two dots over here, there's two edges, but we treat it as one node. Why? Because, so the reason why we define the bottom as a node is because there is no circuit elements in between it. So then it's literally just a wire, right? There's nothing in between it. So that's why we can treat it as a node, as one single node. And now we can go back to this diagram here and define the different nodes. So I'm gonna use a different color. So I'm gonna circle it in blue. So this entire part, right? This is one node, right? Because there is no circuit elements in between any of these wires, right? And then this will be another node easily, right? Because there is no circuit elements in between them. It's just flat wires, right? And this one down here and this one over here, these two are also, this entire thing. So these two are also separate nodes, and this one over here is another node, right? Because it separates these two circuit elements. Well, actually these three circuit elements, right? So yeah, let's count them. That's 1, 2, 3, 4, 5. So there's a total of 5 nodes. But what are essential nodes? Well, the keyword is essential. So an essential node is a node that connects to 3 or more circuit elements. So let's evaluate the simpler diagram down here first. So is this an essential node? No, right? Because it only separates two circuit elements. It separates the R1 and the R2 resistor. And then this one here only separates the R1 and the 5 volts independent source. So this is also not an essential node. But what about the node down here? Is this an essential node? No, because it only separates the R2 and the R2 and the 5 volts independent source, right? So in order to, if we want to make this an independent source, hypothetically, we can extend this circuit, right? We can add another resistor here, right? Or we can add like another current source here. And then right now, this will then become a essential node, right? So let's call this R3, and let's say this is 3 milliamps, right? And yeah, so this will then be a non-essential node, and this entire thing will be a essential node. Yeah. So now let's carry that knowledge that we learned here to the actual problem schematic. So we saw that there's only 5 nodes. So let's find out if they're essential or not. So let's evaluate the one over here first. We're gonna work left to right and then top to bottom. So this one over here connects the 18 volt independent source, and then the R3, R2, and R1 resistor. So that's 4 elements, and 4 elements is greater than 3. So that counts as a essential node. And then this one over here, right? This node over here, it connects to R2, R3, R4, R6, and even this this dependent current source, right? So then that's also more than 3, right? That's also 3 or more, I guess, to put it. And this one connects to R4, R5, and this dependent voltage source. So that's connecting to 3 different elements. So that also counts as a essential node. What about the one over here? Again, it connects to 1 element, 2 element, 3 element, 4 elements. That's more than 3, so we call it the essential node. And then the bottom one over here, it connects to 1, 2, 3, 4, 5. So that's also greater than 3. So easily all 5 of these nodes are actually also essential nodes, right? So there is also 5 essential nodes. All right, so why did I want to define what a node is before I talk about essential branches? The reason being that essential branches are basically circuit elements that's in between essential nodes. So we see that there's a total of 11 branches that's separated by 2 essential nodes. Actually, we already did the branches up here in part 8. So there's 11 essential branches, right? Because all of these circuit elements, they're in between the essential nodes. For example, you can define it however way you want, but just for convenience sake, let's say this is node A and node B. They separate this dependent current source, so then that's the essential branch. And you can apply the same method to, for example, this R7 resistor separated by 2 essential nodes, right? So that's easily a essential branch. So now we know what an essential branch is. Okay, so what about problem D? It asks for essential branches with unknown currents. This is going to be the same as part B because we only know the currents at this independent source over here. So we don't know it anywhere else. So 11 minus 1, that's 10, right? So we don't know what the 10 other elements or the 10 other branches current. And what are meshes? So think of meshes as like these windows, right? These windows that you see on the diagram. So each of these windows represents one mesh. So this is mesh 1, 2, 3, 4, 5, 6, 7. So there's a total of 7 meshes. You can think of it as 7 windows, right? But don't ever write windows on your exam. It's just a way to visualize them, right? Now I want to talk a little bit about Ohm's law. So Ohm's law is easily one of the most important concepts that we need to know to solve chapter 4 problems, especially when we use node voltage and mesh analysis, which I'll explain later, and I'll do more examples. So V stands for voltage, right? So voltage. Let me switch back. So voltage. And then I stands for current. R stands for resistance. So what exactly is voltage? it's the difference in charge potential between two nodes. So hypothetically, between this point and this point on the diagram. So hypothetically, between this node and this node, there is a charge difference, right? So that creates a potential, that creates a charge potential between these two nodes, and that is what the voltage is, right? But what is current? So currents are kind of like the velocity of charges, how fast a charge moves. And resistance, as the name suggested, kind of dictates how difficult the charges can move from node 1 to node 2, right? So if you want, you can think of it this way. So let's say this is your house, right? And then you're going to your school or campus or wherever. So let's pretend this is like your campus or whatever, right? You can take many pathways, right? So you can go this way, you can go this way, or you can go this way. So we know that walking on the hill is probably more strenuous or more difficult. So we call that high resistance, right? So pretend that you're a charge. So this is you going to school, and you're a charge. As you move through, acting like a current, you move through the hills. In this case, it's more difficult comparing to just walking straight to school on the sidewalk, right? The flat sidewalk. So we call this high resistance, and this is low resistance, right? And then also, if the resistance increases, the current will decrease. If the current increases, the resistance will decrease. Reason being that as you walk in this flat sidewalk, your speed is going to be faster, right? Your speed is going to be faster because there's less, it's less difficult to walk on a flat sidewalk comparing to climbing a hill, right? So then your speed or current will ideally be more faster. And the same way can apply for resistance. So let's say you're going up the hill, right? You're going up the hill, so there's more resistance. So then your speed, your current will actually slow down. So that's something to keep in mind, right? As a ratio. So Ohm's law can actually be look at it as a ratio.